Hi, and welcome to the first lecture unit in the lecture chapter on Gaussian processes. So in this lecture unit, I want to motivate not the Gaussian process model itself, but simply the linear model from a Bayesian perspective. And the reason for that is I want us to go through the motions of Bayesian parameter estimation and Bayesian predictive distribution estimation in a very simple scenario that all of you have seen before. I guess many of you might have even seen before how the Bayesian linear model works, so I'll keep this reasonably short and on point. But I want to do this in a simple scenario before we move on to the considerably harder to understand estimating distributions, scenario of estimating distributions on function spaces instead of simple parameter spaces. Okay, so as usual, we assume that there's a data set available to us of size n with the usual notation, IID observations from some unknown distribution. As I will nearly always consider the Gaussian process for regression. We might talk a little bit about this also for classification, but before we do that, we will always assume a regression scenario. So these yi guys here will be simple scalar real-valued numbers. And for notation, I will use bold y as the vector of all combined outcomes, and I will use capital X as always as an n times p design matrix, where the rows specify my observation feature vectors xi. Okay, so far so boring. Here also on that slide, not that much new stuff is going on, so we will now consider linear regression, very super simple linear regression as a model where y equals theta transpose times x plus some error term epsilon. And we can also write down that model here on the data where all of the observations and outcome get in and the error terms get in superscript index I. Of course, because we are now working from a Bayesian perspective, our parameter vector theta is also stochastic, so it has become a random variable, and it follows a certain distribution, and estimating its posterior distribution, given that we have seen all of our training data, that's actually what Bayesian estimation is all about. And a couple of comments here about this additive noise. So first of all, I will, in this lecture unit, assume to simplify things even more, that this is always Gaussian, that this is zero mean, and that this error distribution here has a variance, which I will simply denote with sigma squared. And as nearly always, these epsilon I terms will be independent of x, so of my features, and they always also will be independent of my parameter vector theta. Now, how does learning the distribution of theta now work from a Bayesian perspective? This should hopefully not be new to you at all. So we want to get our hands on this posterior distribution of theta given our data x and y. And we do that by employing our good old friend, the Bayes theorem. So we kind of turn that thing here around and write it in terms of likelihood, which is the distribution of y given the features x and our parameter vector theta times the prior, which is simply a distribution, our prior distribution over theta, and we divide this by the marginal. And as all of you also hopefully know, very often we can even get away with not writing down this complete exact Bayes rule here. We can just write down posterior is proportional to likelihood times prior, because from an optimization perspective, if we were to, for example, find the maximum a posteriori point of theta, so the point of highest likelihood of the posterior, we don't care about this normalizing constant, which doesn't contain theta. And also, if we have this likelihood times prior available to us, we can also often, through other means, normalize it again afterwards, after we've computed it. So yeah, often we don't really need the marginal. And again, to simplify things here in this chapter, I will now assume that the prior distribution of my theta vector is simply a zero mean Gaussian, and that this zero mean Gaussian has a super simple covariance structure of a diagonal form. So this I here is an identity matrix, and there's this width parameter of my prior distribution tau squared, so the variance. And the larger I set that tau parameter, the less I assume to know about my theta vector a priori. And very often I don't know that much about it, so I'll set this to a pretty large value and then let the data speak. If I know something about my parameter vector, I could center this around a different point and make this a little bit more peaked, but I will not do this here. And now, for all of these assumptions, so assuming I have a linear model, assuming I have a normally distributed error distribution, and assuming that my prior distribution is such a Gaussian, we can now super easily show that the posterior distribution of theta is also normally distributed with that mean component here and with this covariance structure where this matrix A. So let's check whether this is written down in terms you already know. That here comes from my error distribution. This here is simply my design matrix. This is my outcome vector, and the matrix A is simply defined as x transpose x divided by sigma squared plus an identity matrix divided by tau squared. So if you have seen how the estimation formulas look like for the ridge regression model, you should be reminded of that structure pretty directly. And I think later on in a further unit, I will talk about this a little bit more. I'll now keep it at, hey, by using this thing here, this Bayesian formula, we can simply now compute this posterior. And I will show this on the upcoming slides very exactly how that works, and that this is not difficult to do. A few comments on terminology. So I've said that here on the slides that the Gaussian family is self-conjugate, and that's kind of the reason why all of that works out in such a simple manner, and that also the posterior is Gaussian again, and that's kind of just, I don't know, abbreviating terminology for that fact. So we say if the posterior distribution if the posterior distribution is in the same probability distribution family as the prior distribution with regard to a specific likelihood function, then we call these distributions conjugate distributions. And the prior is called the conjugate prior for that specific likelihood. The Gaussian family has the super nice property that it's self-conjugate. So choosing a Gaussian prior for a Gaussian likelihood ensures that the posterior is also Gaussian. And this is exactly what we'll see on the next slides. Before I do that, let's run through a simple visualization of this. So I've chosen here a super simple toy example for 1D regression. So I have just one feature here of my outcome y. I have a toy data cloud here. And on the left-hand side, I'm now visualizing my prior distribution. And in the next step, I'll turn that into my posterior distribution. And I will also nicely show how we can kind of now use that to do online learning and do continuous updates, where we kind of assume that data arrives in a stream into our model, and we update our prior to a posterior. Then we use the posterior again as our prior. We update that with new data points, and so on and so on and so on. And we can nicely see how this posterior distribution then becomes more standard, more focused, and develops over time when more and more data points are considered and arrive. So here, for this simple example, I have just used a standard normal distribution. I hope we can accept that our parameter vector here is two-dimensional if we have such a regression situation, because we have one parameter theta 0 for our intercept, and we have a single slope parameter for this 1D regression example. So taken together, we have a 2D parameter situation here. And this is my prior distribution, which is simply a standard normal. So I guess I might have written an I here for identity matrix instead of a 1. I mean, in a realistic scenario, I probably should have used a wider prior variance. So one is might be considered, I don't know, too informative to Senate, but as I said, it's a toy example anyway. And here on the right-hand side, I'm visualizing the maximum a posteriori, or simply, the maximum a posteriori point as a function or as the linear model that it encodes. So with that, I mean that here in my prior distribution, which, like I said, in the next step will then be turned into posterior, there's usually always a point of highest likelihood. At the moment, this is the 0 origin, and the parameter vector here, theta, I will now use and plot the associated linear model on the right-hand side as this orange line. So this here is simply the 0 model. Now I will pick 5 points from my data set, disregard all of the others, and do the posterior computation through Bayes formula. And you can see how this posterior is now peaked around a different point, where you can see the corresponding orange linear model line here on the right-hand side. And you can see that it has also focused a bit more around this MAP point. And I can do this by taking into consideration 5 more points. And instead of now recomputing everything, what I can nicely do is I can take this posterior here that I've computed after observing 5 data points, pretend that this is my new prior, and now run the update only for the subsequent next 5 points. And you can see how this begins to converge to a certain MAP around here, and the posterior distribution becomes more and more peaked and focused around this point. We can now prove that what we did before, that this formula is really correct, and how we can derive that. I'm doing that here on the next slides. So assuming that our Gaussian prior looks like this, as we have assumed before, and assuming that we have a Gaussian likelihood, and this assumption for this Gaussian likelihood is a simple consequence of our assumption of 0 mean Gaussian error terms, epsilon. So we know that y equals theta transposed times x plus epsilon. So if theta is normal like this, and if my epsilon terms are 0 mean Gaussian, then you can easily check that adding these two things together arrives at such a Gaussian likelihood. I guess this is something that you might want to formally check before you start here with the proof. And now what we can do is we can simply use the Bayesian formula. I'm already using this here in its proportional form. So this is the posterior is proportional to likelihood term times prior. And I'm not going to read out these individual steps. I mean, follow this with pen and paper, or hopefully you can just simply read it on the slides and check that all of the steps are super simple to follow. So I want to mention 2 things. Because this here is Gaussian and because this here is Gaussian, you are multiplying 2 exponential terms of very, very similar structure. And then it's already, I think, from this line, it's easy to see that we'll probably end up again with something that again looks like a Gaussian. So the only thing we have to do is we have to reorder terms a little bit. We have to suppress certain constants. And then at the end, we'll still end up exactly with a Gaussian likelihood here of that form. And it's just a little bit, I don't know, wouldn't even call that technical. It's just a little bit cumbersome of reordering these terms and kind of massaging the whole formulas until we end up with the correct structure. But I have chosen to write this really down here in detail, so you can follow this if you want to. You can see that this is really not hard to do. Yeah, and at the end here we arrive at the exact formula that we want. Now, we have now at our hands this very nice posterior distribution for our theta vector. So everything, every kind of, I don't know, stochastic aspect that we might be interested in regarding theta, we can now easily compute from this. Yeah? But we can even do more. We can now derive also the predictive distribution for the distribution of an outcome at a new test observation x star. Yeah? So normally from a frequentist perspective, and for nearly all of the other machine learning models that I've until now introduced here in this lecture, or even will introduce later, the only thing we can usually do is we can plug these x star feature vectors into our model equation f hat and then compute a point estimate for the prediction. Yeah? From a Bayesian perspective, we can now compute easily a complete predictive distribution, which is super valuable for extra subsequent analysis and computation. How does that work? Well, easy, right? So how do we compute the outcome? So the outcome is simply computed by doing theta transpose times x star, right? So this is now given and fixed, but this theta vector here, we know how that's distributed, right? That's the random variable and that's normally distributed. So what we're basically doing here is we are doing a linear transformation of this guy, of this Gaussian. And we know a lot, or we know how easy that linear transformation of a Gaussian is. So first of all, we know if we do a linear transformation of a Gaussian, also for a multivariate Gaussian, that's the result of that is again a Gaussian. So that helps us already a lot. The next thing we know is we know how the mean vector of that Gaussian is transformed. So we know under a linear transformation, pick the old mean vector, which is this guy here, and just apply the linear transformation to it, and you arrive at the mean vector of your new transformed Gaussian. So we take this guy here. In this case, apparently we transpose it, yeah? And then we multiply it with x star. I guess what you could have also done is you could have taken this guy and you could have also multiplied it from the left-hand side with x star transposed. And now for the second component of our output Gaussian, we have to write down the new covariance structure. And there's also a rule for that that's very simple to follow. Pick the old covariance matrix, multiply it from the left-hand side with x star transposed, multiply it from the right-hand side with x star, and that's your new covariance matrix. And that completely now fixes and specifies the predictive distribution of y star at a new point x star. So again, visualizing this a little bit for our toy example. So we have used 5 data points here. And now at each point, I'm writing down or visualizing 2 things. So at each arbitrary test point x, I'm visualizing the posterior mean of my predictive distribution. That's this orange line here. So I'm computing this guy and visualizing exactly this here at x star. And I'm also visualizing the posterior variance. So I compute the posterior variance, and then do a square root of that to get a standard deviation, and then I do plus minus 2 times the standard deviation. And this is this grayish envelope here that you see around the orange line. And I can do this after observing 5 data points. I can do this after 10, and you can see how the envelope becomes shorter and, sorry, not shorter, more focused. Yeah. Centered around the orange MAP. So also not that much new stuff going on here, just visualizing with a simple example what we have learned before. And after 20 data points, even sharper focused. So summary, what have we learned? By switching to a Bayesian perspective, we do not only have point estimates for parameter vector theta, but we have whole distributions. That's nice. From the posterior distribution of theta, we can now derive predictive distributions at arbitrary test points. And we can also do online updates. Whenever data points are observed, we can update the posterior distribution of theta. So we take our current posterior, turn this into a new prior, do again an update of that, and so on and so on. And that kind of allows us to do very simple online stream learning on data streams, or and we can even use that to stream across large databases of many points. But anyway, I want to use all of this here only as a simple demonstration how this Bayesian estimation works. And now I want to move on to more complex parameter spaces where my parameters are not simple distributions over simple vectors anymore. I kind of now want to change perspectives and develop a theory for distributions across complete functions.